as humanity solidifies its capabilities in low Earth orbit and sets its sights back to the Moon. The colonization of Mars represents the next logical and monumental challenge in our expansion into the cosmos. The red planet, with its thin atmosphere, subsurface water ice, and essential raw materials, offers the most viable location in our solar system for a self-sustaining human settlement. This article outlines a comprehensive, updated plan for establishing humanity's first home on Mars, detailing the specific technologies, key programs, and strategic steps required to transform this ambitious vision into a tangible reality. Heavy lift transportation. Transporting the necessary crew and cargo to Mars requires a fully reusable, super heavy lift launch system. The primary vehicle currently positioned for this role is SpaceX's Starship, which is designed to carry over 100 tons of payload to Mars. Its Raptor engines, fueled by subcooled liquid methane and liquid oxygen, are strategically chosen because both propellants can be synthesized on Mars, enabling return journeys. Advanced propulsion for crewed missions. Advanced propulsion for crewed missions. While Starship is designed for the entire journey, NASA is also advancing other technologies to shorten the 69-month transit time for crewed missions, thereby reducing exposure to cosmic radiation and zero gravity. The leading candidate is nuclear thermal propulsion, NTP. Programs like the Diareco demonstration rocket for agile cislunar operations, a partnership between NASA and DARPA, are actively developing NTP systems that could cut the Mars transit time to as little as 45100 days. Martian landing. Landing multi-ton payloads on Mars is exceptionally difficult due to its thin atmosphere, which is not thick enough for a parachute-only landing but too thick to ignore. The proposed method for Starship involves a direct atmospheric entry followed by supersonic retropropulsion, using its own engines to slow down for a controlled vertical landing. This technique is essential for landing the heavy habitats, power systems, and ISRU equipment needed for a settlement. Power first. The absolute first priority upon landing is establishing a robust and continuous power source. While initial missions will rely heavily on solar panels, their effectiveness is hampered by Mars' dust storms and lower solar intensity. Therefore, a compact nuclear fission reactor is the critical long-term solution. NASA's Kilopower project has already successfully tested a prototype reactor, KRSG, designed to provide a steady 10 kilowatts of power. Multiple Kilopower units would be deployed to form a scalable power grid. In-situ resource utilization, ISRU. Living off the land is the core principle of a sustainable settlement. The first uncrewed cargo missions will land a suite of ISRU equipment. A key technology already proven on Mars by the instrument aboard the Perseverance rover, involves converting atmospheric carbon dioxide into oxygen. Water mining. Robotic missions will drill into subsurface ice deposits, melt the ice, and pump the water to a central processing facility. Oxygen and fuel production. The harvested water will be split through electrolysis into oxygen for breathing and hydrogen. The hydrogen will then be combined with carbon from the Martian atmosphere in the Sabatier process to create methane, the rocket fuel for the return journey. Habitat construction. The initial habitat will likely be the Starship vehicle itself, providing immediate radiation-shielded living quarters. Concurrently, construction will begin on a permanent habitat. Rather than relying solely on prefabricated modules from Earth, the strategy will involve 3D printing using local materials. Companies like ISRU are working with NASA to develop technologies that can use Martian regolith mixed with a polymer binder to print structures. This reduces payload mass from Earth and allows for large-scale construction. Closed-loop life support. A successful colony cannot depend on resupply missions for essentials like air and water. The settlement will employ advanced closed-loop life support systems that recycle nearly 100% of all wastewater and purify the air by removing CO and replenishing oxygen. These systems, tested on the International Space Station but requiring much higher efficiency from Mars, are critical for long-term survival. Food production. Greenhouses or biodomes will be among the first structures built. Food production. Greenhouses or biodomes will be among the first structures built. Food will be grown using hydroponic and aeroponic systems, which use nutrient-rich water instead of soil. This controlled environment will protect crops from Mars's harsh surface conditions and allow for a varied, nutritious diet to be cultivated on-site, a critical factor for crew health and morale. The first Martians. The initial crew will be a small, highly trained group of 48 individuals. They will not just be passengers, but active participants in the mission's success, possessing a diverse skill set covering geology, engineering, medicine, and botany. Psychological resilience and the ability to work autonomously as a team in extreme isolation are paramount selection criteria. Supply chain and growth. While the goal is self-sufficiency, early missions will follow a flotilla model, with several cargo starships arriving before the first crew. These will carry the initial power plants, ISRU equipment, rovers, and scientific instruments. As the settlement grows, it will expand with additional habitats, larger power sources, and more extensive greenhouses, gradually reducing its reliance on Earth. The pathway forward. The journey to Mars is being actively paved by current programs. NASA's Artemis program, while focused on the Moon, is the official proving ground for testing the deep space system's life support and operational procedures essential for a future Mars mission, which the agency targets for the late 2030s or early 2030s simultaneously. The aggressive development and testing of Starship by SpaceX aims to accelerate this timeline. Establishing the first human settlement on Mars is the most ambitious undertaking in the history of exploration. It has moved from science fiction to a tangible engineering and logistical challenge being actively solved by both government agencies and private enterprise. By leveraging specific tested technologies like nuclear fission power, in-situ resource utilization, and advanced additive manufacturing, we can create a sustainable, self-reliant home on the red planet. The journey is fraught with immense challenges, from technical hurdles to the profound effects of deep space on the human body. Yet, the methodical progress in these key areas makes the establishment of a new branch of human civilization on Mars not a question of if, but when.